Okay, in this next video, we'll be discussing two sections, 2110, no, I'm sorry, 21.8, Maxwell's prediction, and 21.9, Hertz's confirmation of Maxwell's prediction. So let's get to the PowerPoint and go on to the next one. Next slide. In 1865, James Clerk Maxwell provided a mathematical theory that showed a close relationship between all electrical and magnetic phenomena. His theory unified the separate fields of electricity and magnetism, and it predicted that electric and magnetic fields can move through space as waves. The theory he developed is based on four pieces of information. Number one, electric field lines originate on positive charges and terminate on negative charges. Number two, magnetic field lines always form closed loops. They don't begin or end anywhere. Number three, a varying magnetic field induces an EMF and hence an electric field. The fact is a statement of Faraday's law. And number four, magnetic fields are generated by moving charges or currents as summarized in Ampere's law. The first statement is a consequence of the nature of electrostatic force between charged particles, given by Coulomb's law. It embodies the fact that free charges, electric monopoles, exist in nature. The second statement, that magnetic fields form continuous loops, can be seen in the magnetic field lines around a long straight wire, which are closed circles, and the magnetic field lines of a bar magnet, which form closed loops. It tells us that free magnetic charges, that is, magnetic monopoles, don't exist in nature, even though they're trying to find them. The third statement is equivalent to Faraday's law of induction, and the fourth is equivalent to Ampere's law. Maxwell showed that electric and magnetic fields play symmetric roles in nature. Experiments had already been done that showed a changing magnetic field produced an electric field, according to Faraday's law. Maxwell believed that nature was symmetric, so he hypothesized that a changing electric field should produce a magnetic field. This hypothesis could not be proven experimentally at the time because the magnetic fields generated by changing electric fields are generally very weak and so difficult to detect. To justify his hypothesis, Maxwell searched for other phenomena that might be explained by it. He turned his attention to the motion of rapidly oscillating charges, for example, those in a conducting rod connected to an alternating voltage. These charges are accelerated and, according to Maxwell's predictions, generate changing electric and magnetic fields. The changing fields cause electromagnetic disturbances that travel through space as waves, like the waves created when you toss a pebble into the pool of water. The waves sent out by the oscillating charges are fluctuating electric and magnetic fields, so they are called electromagnetic waves, what I will call E&M waves. From Faraday's law and from Maxwell's own generalization of Ampere's law, Maxwell calculated the speed of the waves to be equal to the speed of light. He concluded that visible light and other electromagnetic waves consist of fluctuating electric and magnetic fields traveling through empty space, with each varying field inducing the other. This was truly one of the greatest discoveries of science, on a par with Newton's discovery of the laws of motion. Like Newton's law, it had a profound influence on later scientific development. And now we'll continue on with Hertz's confirmation. In 1887, after Maxwell's death, Heinrich Hertz was the first to generate and detect electromagnetic waves in a laboratory setting using LC circuits like the one shown here. When the switch is closed, oscillations occur in the current in the circuit and in the charge on the capacitor. If we neglect the resistance of the circuit, no energy is dissipated and the oscillations continue. Let's also assume the capacitor has an initial charge of Q max and the switch is closed at T0. When the capacitor is fully charged, the total energy in the circuit is stored in the electric field of the capacitor and is equal to the potential energy of the capacitor. There it is, PEC equals Q max over 2C. Let's see. At this time, the current is zero, so no energy is stored in the inductor. As the capacitor begins to discharge, the energy stored in its electric field decreases. At the same time, the current increases, and when the capacitor is fully discharged, the total energy is the potential energy now stored in the magnetic field of the inductor. PEL equals Li squared over 2. In this way, energy is transferred from the electric field of the capacitor to the magnetic field of the inductor. The process then repeats in the reverse direction. The energy continues to transfer between the inductor and the capacitor, corresponding to oscillations in the current and charge. As you recall, the frequency of oscillation of an LC circuit is called the resonance frequency of the circuit and is given by the equation shown here. F sub 0 equals 1 over the square root of 2 pi square root, 1 over 2 pi times the square root of LC. The circuit Hertz used in his investigation of electromagnetic waves is shown schematically in the figure here. An induction coil, which is a large coil of wire, is connected to two metal spheres with a narrow gap between them to form a capacitor. Short voltage pulses are sent from the coil to the spheres, charging one positive, the other negative. Because L and C are quite small in the circuit, the frequency of oscillation is quite high, about 100 megahertz. This circuit is called a transmitter because it produces electromagnetic waves. Hertz then placed a second circuit, the receiver, several meters from the transmitter circuit, which consisted of a single loop of wire connected to two spheres. It had its own effective inductance and capacitance, and natural frequency of oscillation. Hertz found that the energy was being sent from the transmitter to the receiver when the resonant frequency of the receiver was adjusted to match that of the transmitter. The energy transfer was detected when the voltage across the spheres in the receiver circuit became high enough to produce ionization in the air, which caused sparks in the air gap separating the spheres. We can think of Hertz's experiment as being analogous to when a tuning fork picks up the vibrations from another identical tuning fork. Hertz hypothesized that the energy transferred from the transmitter to the receiver is carried in the form of waves, which we now recognize as electromagnetic waves. He performed a series of experiments where he showed that the radiation generated by the transmitter exhibits wave properties: interference, diffraction, reflection, refraction, and polarization. All of these are also exhibited by light. It was clear that Hertz's electromagnetic waves had the same known properties of light waves and were different only in frequency and wavelength. Hertz effectively confirmed Maxwell's theory by showing that Maxwell's mysterious electromagnetic waves existed and had all the properties of light waves. Perhaps the most convincing experiment Hertz performed was the measurement of the speed of waves from the transmitter. He did this by directing waves of known frequency from the transmitter so that they were reflected from a metal sheet, so that an interference pattern was set up, similar to the standing wave pattern on a stretched string. As you recall, the distance between nodes is lambda over 2, so Hertz was able to determine the wavelength using the relationship shown here. V equals the velocity equals the frequency times the wavelength. V equals F times lambda. I need to find where I was in the reading. He found that V was close to 3 times 10 to the 8 meters per second, the known speed of visible light. Hertz's experiments provided the first evidence in support of Maxwell's theory. So this ends the 2 section on Maxwell and Hertz. The next section we will discuss is section 2.10, the production of E&M waves by an antenna.